When you look at any complex operation, whether it is a manufacturing plant, a hospital, or a logistics network, you will find an unavoidable variable: human attention. On the left side of this model, we see a system that relies entirely on an operator performing flawlessly, which inevitably yields high defect rates and material scrap. On the right, we have a system where the physical components lock together in a way that mathematically prevents incorrect assembly. A single lapse in attention on the assembly line does not stay localized. If an improperly fastened component moves to the next station, the cost to fix it multiplies. By the time that localized error reaches the final consumer, it results in massive systemic losses through warranty claims, physical waste, and consumed capital. Early industrial systems operated entirely on the assumption that workers could maintain perfect focus. Production lines relied almost completely on human perfection to maintain quality control, with operators manually verifying every step. As production scales into the millions of units, requiring absolute human infallibility becomes a statistical impossibility. The mathematics of probability guarantee that an operator will eventually misread a dial, skip a step, or install a part backwards. High-reliability organizations recognize this math. They do not achieve quality by posting warning signs or demanding that their humans try harder. They achieve it by engineering the vulnerability out of the system entirely. Modern quality management requires a shift in how we view mistakes. Instead of building reactive correction systems to catch errors after they occur, the goal is to build a preemptive architecture that physically intercepts the error before it can form. The first conceptual layer of this architecture is mistake-proofing. This is a preventive framework designed to guide user behavior and minimize the probability of human error through clear instructions and standardized processes. The next structural escalation is foolproofing. Here, the design is altered so that making the error becomes physically impossible, taking the choice entirely out of the user's hands. On the factory floor, these concepts are operationalized through a specific Japanese methodology known as Poka Yoke, which translates directly to mistake avoidance. Mastering mistake-proofing, foolproofing, and Poka Yoke provides the exact mechanical pathway an operation needs to transition from accepting a baseline failure rate to running a true zero-defect manufacturing environment. System safety exists on a spectrum of control. You rarely jump straight to absolute perfection. You begin with partial interventions. Mistake-proofing sits on the partial end of this spectrum. It is a procedural approach that gently guides the user. It warns them, but it cannot physically stop a deliberate action or an act of severe negligence. We interact with this level of control every day. When an ATM dictates the specific direction you must insert your card, or when a computer system forces you to include a capital letter and a number in your password, you are experiencing procedural mistake-proofing. The limitation here is clear. These rules reduce the frequency of errors, but the architectural vulnerability remains intact. A user can still ignore the instructions and force the card in backwards. Foolproofing corrects this by pursuing absolute control over the interaction. It operates at the fundamental design level. By engineering the exact geometry or logic of a system, foolproofing ensures the user cannot fail, regardless of their intent or behavior. Look at the interlock on a microwave oven. The machine is designed to mechanically sever its own power supply the moment the door is opened. You do not have to remember to turn it off. The physical barrier makes accidental exposure impossible. This matrix outlines the differences. Objective: mistake-proofing minimizes errors. Foolproofing makes them impossible. Control: partial guidance versus full mechanical authority. Crucially, mistake-proofing is applied downstream during production, while foolproofing is embedded upstream at the fundamental design level. Upgrading a process from mistake-proofing to foolproofing lifts the burden of accuracy off the human mind and permanently transfers it to the physical geometry of the tool. To see how this theory functions under industrial stress, we look to Poka Yoke mechanisms on the active factory floor. A zero-defect environment is a minefield of safety mechanisms, categorized into 5 types of operational control. Station 1 represents the warning type. It relies on immediate sensory alerts, like flashing beacons, to notify an operator of an anomaly. Station 2 utilizes the control type. This aggressive intervention autonomously halts the conveyor line upon detecting a fault. Station 3 demonstrates the contact method. By utilizing physical constraints or precisely cut jigs, the workstation blocks an incorrect part. Station 4 employs the fixed value method, enforcing strict quantitative control. A sensor verifies the exact number of screws dispensed. Finally, Station 5 is the motion step method. It enforces sequential verification, physically blocking Step B until Step A validates. These industrial mechanisms operate in our homes as well. The auto-ignition requirement on a modern gas stove forces you to press and hold the dial before turning it, a domestic application of the motion step method that prevents catastrophic gas leaks. By layering these 5 mechanisms together, engineers weave a localized web of infallibility around a single operator, covering sensory, mechanical, and sequential vulnerabilities. Achieving a 100% yield on a production line is not a matter of luck. It is the mathematical outcome of deploying the correct Poka Yoke taxonomy at the exact point of human vulnerability. Deploying these mechanisms requires an organization to follow a rigid 6-step engineering protocol, which begins with the meticulous collection and analysis of existing defect data. Step 2 requires root cause analysis. You cannot engineer an effective constraint until you isolate the exact origin of the failure. Engineers map this using a fishbone diagram, separating variables like machinery, raw materials, and human methods. Within that map, they apply the 5 whys technique, a recursive interrogative method used to strip away the surface symptoms until the base mechanical or logical flaw is exposed. Steps 3 and 4 are solution design and tool selection. These are directly dictated by the root cause. If the flaw is geometric, the solution is a contact method jig. If the flaw is sequential, the solution is a motion step digital lock. The final steps are physical implementation and retraining. The workforce must be recalibrated to understand how to operate alongside the new constraints without trying to bypass them. Skipping root cause analysis to blindly install expensive sensors across a factory is merely treating the symptoms of a poorly designed architecture. An implemented solution remains a hypothesis until it is mathematically verified in a live production environment. Engineers subject the new mechanism to extreme stress testing, pushing the component to its operational limits to ensure the barrier holds up under sustained friction. Following the physical tests, continuous data analysis is required to track the trajectory of defect rates over time. The numbers must prove the intervention is working. This data is supplemented by routine physical audits and direct operator feedback, which highlight behavioral edge cases that the engineers failed to predict during the design phase. Finally, the system's viability is judged against key performance indicators. Management tracks the ratio of quality improvements directly against the total capital cost of implementation and maintenance. This closed-loop verification process proves the return on investment. It directly translates prevented errors into saved capital and preserved resources. Achieving structural infallibility introduces significant new frictions into an organization. The transition to absolute control is rarely smooth. It requires steep upfront capital costs and intense technical complexity to integrate advanced sensor networks into legacy machinery. On the floor, it can trigger resistance. Operators often view rigid physical constraints and forced sequences as a lack of trust in their skill, leading to hesitation and workflow disruption. There is also the ongoing burden of mandatory maintenance. If a delicate Poka Yoke sensor breaks down or miscalibrates, the control-type mechanism will halt the entire production line unnecessarily, costing thousands of dollars a minute. These challenges are the necessary operational overhead required to sustain a world-class standard. They are the price of precision. When fully integrated, chaotic production snaps into order. Physical constraints lock the workflow in perfect alignment. Downstream, rework disappears, warranty claims plummet, and defect rates drive steadily towards zero, resulting in a surge of client trust. It is vastly superior, in both economics and engineering, to stop a mistake before it happens than to repair the damage afterward. Mistake-proofing, foolproofing, and Poka Yoke represent a shift in how we build the modern world. They prove that operational excellence is not achieved by hoping people do not make mistakes. It is achieved by building perfection into the architecture itself.